Alright, hi y'all. I'm going to be doing this EM Waves Fall 2020 exam. And if you want to follow along, you can go to the course webpage. They have this problem here. I'm only doing this first one because the other two are about transmission lines and time domain, which we haven't gone over in class, so I'm not going to be going through that here. This is your typical coaxial cable region, which is a cylinder. And we're trying to find the magnetic field vector in the phasor domain, the electric field vector in the phasor domain, as well as the complex power and the watts and reactive power in VARs going downward through the surface, which is important. The direction is very important. So here we can read the problem. Fields exist inside of a coaxial type of region that is described in cylindrical coordinates, so make sure it's not rectangular, so we can't just default rectangular coordinates. The fields exist in the coaxial region A to B and 0 to 2 pi, and of course Z 0 to L. So we're on the XY plane, protruding into that Z axis, the positive Z axis, of course. Now this region is non-magnetic. Okay, cool. So what that means is mu is equal to mu naught, and it has a relative permittivity E epsilon r. So we can write that a little nicer, epsilon r. The magnetic field in this region is given by this equation, and it only has a phi hat. So it's only in the phi hat direction. That's totally fine. The first question, or first thing it asks, is find the magnetic field in the phasor domain. Okay, well, how do we go from time domain to phasor domain? Let me rewrite the equation here. So H, make sure you put this vector symbol, this line underneath. At least I don't know if he's going to take off points, but you can never be too sure. So let me redraw this. Phi hat times 1 over rho cosine of kz and cosine omega t. If we want to go from time domain to phasor domain, remember phasor domain is more of a snapshot in time, meaning we do not have a time constant, time value in phasor domain. So we need to get rid of this specifically. How do we get rid of it? Well, one way we can get rid of this is, well, we can change this into something with the j component. Well, we know cosine omega t, it has this phase shift equal to 0. So e to the j theta is the same thing as cosine omega t. Or using Euler's formula, you can use cosine omega t plus j sine omega t. In this case, there's no sine omega t, and there's no phase shift here. So this is equal to a to the j0 is equal to e to the 0 and equal to 1. So what this tells us is the magnetic field vector in the phasor domain is equal to phi hat 1 over rho cosine of kz times 1, of course, but we don't have to put that 1. It doesn't matter. But this would be your answer for part A. Part B, it should ask, what is the electric field vector in the phasor domain? So in practice, this isn't difficult. Whenever we did homework 2, I believe, it asks to go from the electric field to the magnetic field. And what did we do? We said the curl of E is equal to negative partial T times B vector. Now, we have this very similar equation where it goes the opposite ways, namely Ampere's law. In Ampere's law, we'll put B here. Ampere's law, it states that the curl of H is equal to some free current in free current plus the partial with respect to t of d here. What is d? D is the electric displacement field, and J is the free current density. Okay, well, we have no clue what this j is. There's no way we would know this. It doesn't give us anywhere in this problem. One thing we do know, though, is we are in a coaxial type of region. We are not in a coaxial cable. So there's not going to be current flowing through this. It's just saying that in free space, let's say, for example, in free space, we have this cylinder type of space. I don't know, region, whatever you want to call it. But it's not a coaxial cable, so we can deem it as free space. Note, in free space, that free current density is equal to 0. So what we can do is we can say this is 0. Something else to note. What is D? D is the electric displacement field, also known as epsilon E. This is how we get the relationship between the magnetic field vector and E. So that would be how we end up getting this equation. All right. So let's rewrite this. This is equal to partial with respect to t epsilon E vector. Now we're in the phasor domain. How do we change? Remember, we don't want any times. Time should not be here. How do we change partial of t to make sure it's a frequency, or in phasor domain, which again is frequency domain? What we do is we change this partial to j omega. So then what this is equal to is j omega epsilon E vector. Now we want to solve for the E vector. Let's solve for it in letters first. So the E vector is equal to the curl of the magnetic field divided by j omega epsilon. Now we can leave this as is. Of course, we had to find this curl of H. Okay, so let's find the curl of H. Hopefully y'all are following so far. These are basic equations we need to know. Of course, we haven't gone through very many practice problems. We definitely haven't gone through enough. I don't think we just kind of goes through. So what I would recommend is doing some of these practice problems and getting familiar with these Maxwell's equations, because he could ask anything on the exam, and if you don't know that, oh, in free space that charge is going to be 0, or this current is going to be 0, this is important, because he could definitely put this on an exam, and he could either specify that there is current flowing through this cylindrical region going from bottom to top or top to bottom. We have to know what exactly it's talking about. What are we going to put for this J value? Anyways, let's take this here. So this is going to be, again, we are in cylindrical coordinates. So let me pull up the cylindrical coordinate matrices. So what we have is rho hat. Of course, this is 1 over rho. We have rho hat, partial of rho, and then we have h of rho. Does this have any rho in here, rho hat? No, so this is going to be 0. Okay, well now we have rho phi hat. Okay, does it have a phi hat? Yes, it does. So we're going to go here. This is the partial with respect to the phi hat. And now we write out our phi hat here. But this is rho times unit vector phi hat. We don't have that here. We need to make sure to multiply by rho. Sorry. So now it's 1 over rho cosine of kz. Hope y'all can see why I multiplied by rho. It's in the notes here that you have to multiply by rho, but it's mostly because we only have a phi hat right here. We want it in the form of rho times phi hat. So what we do is we multiply this by rho, and we can say this is just rho. Easy enough. Now we do the z hat component. This is the partial with respect to z, and there is no z component. So now what we do is we can find out that this we take here, so we have rho hat times this times 0 is always 0 minus partial with respect to c times rho times 1 over rho, that's 1. So then we have just the cosine of kz. Now we do minus rho phi hat times, okay, let's take this out here. We have dd rho times 0, that's 0. ddz times 0 is 0. Okay, so let's just replace that with 0. Plus the z component of, let's cover this. We have dd rho times cosine kz apparently. So we have dd rho cosine kz minus dd phi times 0 is 0. Hopefully y'all have made sure to keep up with this. Let's start over here. This is going to be what? That's 0. There's no rho to evaluate this derivative. So this is 0. So we have this is 0, this is 0. We're left with the rho hat. So the curl of our magnetic field is equal to rho hat 1 over rho. Remember this 1 over rho here. We can't forget this. 1 over rho, the derivative of cosine kz, negative by the way. So derivative of cosine kz is negative k sine kz. Take out this k here, move it to the front, and derivative of cosine is negative sine. So we have a negative times a negative is a positive, and we have k sine of kz. Hopefully y'all kept up with that there. This is just a derivative. We can let, if you want to just think about it as ddx, let z equal x. Derivative of cosine is negative sine. Do chain rule, move this to the front. Okay, so we have our curl now. Look at this equation here. We have our curl over. So what this is saying is that the electric field vector is this. So we can say rho hat k sine of kz divided by rho j omega epsilon. Now, we don't know what epsilon is. We know what epsilon r is, and we know what epsilon 0 is, but we don't know what epsilon r is. So what we must do is let epsilon equal epsilon naught times epsilon r. This is in a set of notes that he kind of skimmed over. Make sure to replace this epsilon with epsilon naught times epsilon r. That should give you the right answer. Let me make sure and check before I finalize that. K over P. Okay, yeah, it's looking right. They left it just like that. And actually they moved that K, or they moved this J up to the top, and they let it be negative J. Rho hat K over P. Okay, yeah, that's right. Okay, cool. So we can leave it like this. Make sure you don't forget your units, volts per meter. All right, so now that's part B. What is part C asking? Part C, if I remember correctly, is asking for the Poynting vector. And it's asking for complex power. Complex power is the Poynting vector, right? But we have to take the integral, the surface integral of it. So first thing we have to do is get that Poynting vector. So this is part C. Let's find out what that Poynting vector is. Well, we know S is equal to, Poynting vector is equal to 1 over 2 electric field crossed with the magnetic field conjugate. Okay, well, what does the conjugate of the magnetic field? Let's go back here. Let's find that, what H was. H was this here. Okay, what does the conjugate do? Well, what the conjugate does is it flips your phase angle to negative. of that value. So what we must do is change every j to its opposite. In our case, we have no j's in this h. We know h is purely real. So what is the conjugate of h? Conjugate of h is just h. So conjugate of h is then this unit vector, phi hat, 1 over rho cosine of kz. Okay, but we also know E. E is what we had gotten before, so let's take the cross product. So E cross H conjugate is equal to, okay, going back to our cylindrical coordinates, we're doing another matrice. We have 1 over rho, make sure not to forget this. We have rho hat. Okay, what has rho hat? Well, our E has rho hat. Okay, that's pretty good. We can leave that there. We have k over rho, and then we can put this whole thing j omega epsilon naught epsilon r k sine of kz. Okay, that's what we have here for E. Now H, does it have a rho hat? No, it has a phi hat, which is the next one, rho times phi hat. Does E have a rho hat? No, or a phi hat, I'm so sorry. No, it's 0. Now, does the H conjugate have a phi hat, which is this unit vector here? Yes, it does. But we have to make sure to multiply by rho because we have to make sure it matches this rho times phi hat. If you don't understand that, that's totally fine. Go off the notes. It says to multiply your the phi component by rho. This is how I remember it. If it doesn't match, make sure to multiply by rho. If you don't remember it like that, that's totally fine. Just make sure to write it into your notes. It's very important. This is 1 over rho cosine of kz. And then we have our zth component. This is 0 and 0. There are no z components. Now this is equal to, let's get our unit vector out here, rho hat. Cover this. We have 0 times 0, so that's 0, minus 0 times whatever this is, that's still 0. So we have no rho component. Minus our phi, or our rho phi hat component. Okay, let's cover this. This times this is 0, minus this times that is 0. That's 0 still. Sure. Plus z component. Okay, let's cover, oops, my bad. Let's cover this here. We have z component. This times this, that's what we want. Okay, rho times 1 over rho is 1. So we're left with cosine kz for this one. But then we have k over rho, we can put the j out in front, omega epsilon naught epsilon r sine of kz cosine of kz minus 0 times 0 is 0. So we cannot forget this, by the way. This 1 over rho is very important. So what we're left with now is we're left with S is equal to 1 over 2 times 1 over rho. Remember, this 1 over rho must come down, times this whole entire thing. This is 0, that's 0, but this is left here. Oops, sorry. That's 0, this is 0, and this is left here. Now, we multiply that and make sure it's in the z unit vector direction times all of this stuff here. So k sine of kz over j rho omega epsilon naught epsilon r. I didn't miss anything. Oh, cosine kz, my bad. Cosine kz, make sure that gets in there. So this is our Poynting vector. Rho times rho is rho squared. We can put that there. Now, it's asking for the, what is it asking for? It's asking for the time average power in watts and reactive power. Okay. Okay, well, how do we get complex power? Because this isn't complex power. This is the Poynting vector. But we said we got the complex power by doing what? Well, we have to take the surface integral, so complex power denoted by P is equal to the surface integral of our Poynting vector. Make sure to put this there. Oops, messed up. Times the normal vector. But remember in the very beginning, it says the normal vector is downward sensed. So this means we have a negative normal vector. Because upward is our sense of positive. Okay, so we have times, this is negative z hat, and then ds. This can be rewritten as the double integral negative. We'll move this negative out in front. We'll make this negative here. So now this is a negative instead. Negative, the integral from 0 to 2 pi and from a to b. This is your cylindrical integral, surface integral, of the Poynting vector times rho d phi. And this is the Jacobian whenever we have a double integral. We have this rho d rho. So what is S? Well, this is equal to the negative double integral of 1 over 2 times 1 over rho squared times k sine kz cosine kz divided by j omega epsilon naught epsilon r. And all I'm doing is I'm just moving this over here now. And this is rho d phi. This is from 0 to 2 pi, a to b. Hopefully y'all can see what I'm going with here. All I did was plug in everything we know. Now, remember this rho here has to be multiplied to everything. Rho times 1 over rho is 1 over rho. Okay, and everything here is not a function of rho. That means we can take it out. So now we have P is equal to negative K sine KZ cosine KZ over 2, we'll put the J out in front here, omega epsilon naught epsilon r. And then the double integral of 1 over rho d phi. 0 to 2 pi, a to b. So what we do is we take the outer integral first. So the outer integral here, the integral with respect to rho is, that's just rho, or phi, I'm sorry. The integral with respect to phi is just phi, so you just have 2 pi minus 0. So then we'll take this first. This is equal to, I'll just rewrite this, 2 pi times the integral from a to b of 1 over rho d rho. Well, the integral of 1 over rho, or 1 over x, is natural log of x. So we have 2 pi natural log of rho, or b minus natural log of a. We can rewrite this to be equal to 2 pi natural log of b over a. This is using log specials, whatever you want to call it, like rules. So what this would be equal to is the 2's here. I'll show you the whole thing here. Negative k 2 pi, we're moving that 2 pi up to the top, sine of kz cosine of kz divided by j2 omega epsilon naught epsilon r times natural log of b over a. So this we can leave as complex power if we want. We can also cancel out the 2's here, and that would be the equation. Now it's not asking for complex power. Technically it is, but it's asking for the time average power in watts and the reactive power. Well, power in watts, so we'll say PW, is equal to what? It's the real part of our complex power. And then the reactive portion, or our Q, is equal to the imaginary portion of our complex power. Now, looking at this, we have what? We have J. That means this entire part here is imaginary. This is only imaginary because if we move the J up to the top, even if we don't, you can see here it's a multiple of J. This is J times something. There's no real portion to this. So, now what do we know? Well, we would then know that the real portion is 0, and the imaginary portion is just this, without the J. That would mean we'd have to move this to the top, pretty much. Sure, I guess we could move it to the top. So let's move that to the top. We get rid of this negative, and there we go. We move that to the top. We get rid of the negative. We let J be there, but now this is K pi sine of KZ cosine of KZ times natural log of B over A divided by omega epsilon naught epsilon R. This is our entire equation. Also, we can't forget that this is a Z component just from over here also. All right, but that tells us, make sure this is in watts and VAR, of course. This is our answer. So hopefully that makes sense. That's how we do this problem, example 1, or problem 1 from the fall of 2020. Hopefully this all made sense and you can replicate this. Make sure to practice over this kind of stuff. Look back at past exams. I'll be going over some of these before the first exam. Whenever the exams start coming up, maybe 2 weeks before, I'll start ramping up the videos, maybe. I'll definitely start studying a little more. So hopefully that was helpful. If you have any questions, make sure to ask them. If I messed up anywhere, please let me know. If you have any questions, again, ask me. If you need anything, just comment it down, and I'll try to get back to you whenever I can. All right, well, hopefully that was helpful. Thank you.